thank you very much, Bill, and thank you very much for inviting me here. I see a lot of familiar faces, and you may have seen some of this talk before, but this is going to be a long talk compressed into a short time. Hopefully, I'll keep you interested. I'm going to talk about architectures for intelligent machines. I was actually invited to give a keynote at a SRC funding symposium one time, and I forgot to send my title. And the person who was organizing the symposium saw it fit that I would talk about architectures for intelligent machines. So they titled the talk Architectures for Intelligent Machines for me. And I thought, this is a great title, but it's missing something. It's intelligent in the beginning. So I put intelligent architectures for intelligent machines at the beginning. So I've been giving this talk for some time now. And I think I really like it. I like this title. Okay, so I'm going to talk about, again, the problem right away. I think today, computing is bottlenecked by data. And data is really key for all the interesting workloads that we have. AI, ML, genomics, whatever you're interested in, they're all data intensive, and they require rapid and efficient processing of large amounts of data. And data is increasing. We can generate more data than we can process today. You can see some of these workloads over here. They're maybe on the data center scale, but data is a performance and energy bottleneck in them. If you go to the, I don't want to call this a lower end because some of the highest performance computing machines are built in these small devices. And data is a performance and energy bottleneck in these devices as well. And if you look at emerging applications like genome sequencing, today we can generate a lot more data than we can process because the cost of genome sequencing is actually reducing a whole lot faster than the cost of a transistor today. And as a result, data becomes a performance and energy bottleneck in genome analysis, which could enable a lot of innovation in the world, in my opinion. And this is an area that's close to my heart. We do a lot of work in this area. I'd be happy to talk about it too. But that's not the subject of the talk. But you can see that there are devices that are generating a lot of data today, and this is one a genome analysis, genome sequencing device that you can buy for $1,000 or $2,000. You can actually do your genome analysis yourself. Actually, people are using this device in Africa, for example, to sequence viruses. And what they're doing is, because you don't have capability to process data locally on the device, and the data is so large that you have to actually send it to a data center all the way to Europe or China or US, wherever, to process it. So we actually are able to generate data very quickly, and if we had the capability to do process data locally where the data resides, we could be a whole lot energy efficient. Okay. So basically today, data overwhelms modern machines. It overwhelms the storage and memory capability, communication capability, and in the end, the computation capability as well. It greatly impacts robustness, energy, performance, and cost. And if you look at a computing system, it consists of three key components: computation, communication, and storage. And we've been heavily optimizing the computing units, but we've kind of been ignoring the data storage and movement units. Of course, take this with a grain of salt, right? Ignoring is a strong word, but clearly we put a lot of effort into the computing units. But if you look at a node, a system today, most of it is really, this is a single node. If you look at the macro scale, the picture is actually relatively similar. In a single node, most of the system's resources is really dedicated to storing and moving data. If you do the calculations, more than 90% of the single node is dedicated to, its area is dedicated to units that store and move data. Less than 10% is computation, and we call these computing devices. They should probably be called data storage and movement devices today. But I will hopefully show you that this is because of the way we've been designing architectures. Okay, so as a result, data overwhelms modern machines, and we recently done this study with Google on their small devices, and we found out that on these four important workloads that I showed you earlier, more than 60% of the total system energy is spent on data movement, solely moving the data inside and outside the processor itself. Okay, so my axiom is because data is so important today, an intelligent architecture has to handle data well. So what does it mean to handle data well? I believe this requires ensuring data does not overwhelm the components, meaning we need intelligent algorithms. We also need intelligent architectures, and perhaps more importantly today, we need intelligent algorithm architecture device co-designs across the stack, whole system. That's number one. The second one, we probably want to take advantage of vast amounts of data and metadata that we have, that the computing system is exposed to. This phone was built 5 years ago, and it's still doing exactly the same thing it's doing in its memory controller, its cache, its all of its components actually. It hasn't learned a thing in those 5 years. It hasn't adapted its policies to what it has seen in the 5 years. It's essentially forgotten. But intelligent beings like us, hopefully we learn stuff within the course of minutes, not just 5 years, right? So this is not an intelligent architecture, basically. The key is how do we actually get into an intelligent architecture so that we can take advantage of vast amounts of data and metadata to improve architectural and system level decisions. And on top of this, I believe we need to understand and exploit properties of different data. We're not very good at this today because architectures actually do not know the different properties of data. We don't know the security properties of different data. We don't know the approximability or compressibility properties of different data, for example. Can we actually incorporate this into the design and to improve the algorithms and architectures and various metrics? So in this slide, I will deconstruct architectures. By the way, please do not try to read my slides. It's better to follow me talk and try to get the key things from the slides, otherwise you will be overwhelmed with the slides. These slides will all be available in the end. So I will have three corollaries based on these axioms. Essentially, today's architectures are terrible at dealing with data because they're, as you can see, we call these computing architectures, but they're mainly moving and storing data. This is because they're based on the processor-centric paradigm as opposed to a data-centric paradigm. Data is not the key thing we design architectures around today. It's really the processor that we design the architectures around. The second thing is architectures are not able to take advantage of the vast amounts of data that's available to them. They basically make very simple decisions ignoring lots of data because they're designed in a human-driven manner as opposed to a data-driven manner. Whenever you design a memory controller, for example, a human designs it, and a human can do only so much. It's a very multi-dimensional state space where you need to consider a lot of state variables and changing workloads if you really want to come up with a good policy. You really need to be data-driven in this case. I'll hopefully give you an example of this later on. And finally, architectures today are terrible at knowing and exploiting different properties of application data because it's not communicated to them. They treat data all the same. This is because, as a result, they make component-aware decisions as opposed to data characteristic-aware decisions. Hopefully this will become a little more clear. So I'll try to go through each of these with some level of detail, maybe spend more time in the first one over here. So basically today we're processor-centric. Can we actually move to a more data-centric or memory-centric architecture? So then the key question is, of course, what are the properties of a data-centric architecture? I think the first one is you need to process data locally where data resides. We want to minimize the movement of data, but the other ones are also important. We want to enable low latency and low energy access to data. I don't think we're doing very well in that one. Today's memory architectures are, for example, very much designed for capacity, and they ignore latency in many of the decisions, and as well as energy too, because latency is very much correlated with energy. We want low-cost data storage and processing and intelligent data management. I'm going to touch upon mainly the first one over here because I think this actually enables a lot of the other ones later on, even though they're somewhat orthogonal in different cases. Okay, I call this processing data where it makes sense, basically where the data resides. So why is this interesting? These are three key system trends as I see them. Basically today, data access is a major bottleneck. I'm going to show examples of this. And energy consumption is a key limiter, and data movement energy dominates computation energy today. This is especially true for off-chip to on-chip movement. In my opinion, the key question is this: do we want a world going forward that looks like this, or do we want a world that looks like this? I would probably pick the previous one. But we also want that world, we want an energy efficient and sustainable world, but we also want it to be high performance. What is the problem? Data access is a major bottleneck today. Our design principles, our current design principles cause great energy waste. We're very far away from that world because we're moving data all around in the micro scale as well as in the macro scale. They cause great energy waste. They also cause great performance loss. Basically, data is processed. Data has to be moved to a processor far away. That's a lot of energy. And to overcome that latency of data movement, we actually add a lot of mechanisms into our systems to tolerate data movement. Multi-threading, caching, prefetching, whatever favorite technique you want, out-of-order execution. These actually make the system even more complex. They cause even more energy waste. So we're in this vicious cycle today. We're moving a lot of data that causes energy waste. We're trying to tolerate that with even more energy waste and complexity. So we actually need to get out of that vicious cycle somehow. Of course, whenever you're in a vicious cycle, you need to first understand what is the cause of the vicious cycle. And I believe in this case, the cause is this: processing of data is really performed far away from the data. And once you understand that, the question is, of course, how do you solve that problem, right? I showed this picture earlier to you. I'm not going to go through this again. But basically, the problem is really the processor-centric design paradigm. We've heavily optimized the processor. We know actually how to do processing really well. We've been building accelerators, processors very efficiently. But maybe we're not treating the data in the right way. But we also know that memory is the big bottleneck. This is Dick Seitz. After he designed the alpha processors with his team, he basically said that it's really all about the memory because we designed this processor to finish 4 instructions every cycle, but this processor is finishing one instruction every 4.7 cycles. It's operating at 1/18th of its peak memory peak bandwidth, basically, peak processing bandwidth. And this was the fastest processor of its time, by the way, in 1990s. And he basically ended this one-pager paper. I would recommend that everyone take a look at this. It's a beautiful paper. This is a person who dedicated his life to building processors itself with this sentence: I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. And I think this is actually interesting. I wouldn't put probably only, but I think it makes a point. And this is data from my own PhD thesis later, fast forward 10 years later. We looked at Intel workloads, and we showed that basically more than 50% of the time the processor is waiting for data. It's not doing useful work. Okay, you don't believe me, you don't believe Dick Seitz. Since everybody believes Google, I use Google's paper. This was published in 2015. They basically analyzed all of their data center workloads, and they showed exactly the same thing. In the state-of-the-art processor, the processor is waiting for data. It's not doing anything. It's actually doing useful work only 10 to 20% of the time. Skip these. Essentially, this situation is there because we have a grossly imbalanced system. Processing is done in only one place. As a result, data moves a lot. As a result, we're energy efficient, low performance, and complex. And to tolerate this, we make the system even more complex. And we have this picture in the end. Most of the system is dedicated to moving and storing data. Let's look at the energy perspective very quickly. This is data from Bill Daly, High Peak 2015. You can argue with all of these numbers because they're relatively old, but the trends still remain the same. This is a complicated double precision floating point operation, 20 picojoules, a memory access, 16 nanojoules. It's almost 3 orders of magnitude. If you actually optimize it, it's about 2 orders of magnitude. In existing systems, it's about 2 to 3 orders of magnitude. There was actually a special session in DAC on AI accelerators in June, and people were giving out numbers. One person was generous enough to give the number in terms of the energy cost of a memory access versus a floating point multiply and add in their AI accelerator, and he said that it's 160x in our design. So 1000x, 160x, that's still 2 to 3 orders of magnitude. And as a result of this, more than 60% of the entire system energy in real workloads that we use in our systems is spent on data movement. Basically, we do not want to move data from a performance perspective, from an energy perspective, also from a reliability and security perspective, I think. So what do we need? I believe we need a paradigm shift to enable computation with minimal data movement, to process data where it makes sense, compute where it makes sense, where data resides, essentially make computing architectures more data-centric. So what does this mean? I'm going to take an example of memory over here, but data resides in many, many places in a system. I believe we really need to distribute computation in all of the places where the data resides. If you look at the memory is very interesting because it's large. We can store a lot of things to it. Basically, we would like to be able to talk to memory. We would like to be able to say, can you do this function for me? And if the memory is able to do that, it can return the results. And then they have a handshake, they have some distributed algorithm, they actually can improve the performance overall. Of course, I'm not going to give you all the answers over here. There are many, many questions. How do we design the hard compute-capable memory and controllers in this case? How do we design the processor chip in memory units? How do we design the software and hardware interfaces to enable all of this? They're not there at this point, but I think we'll get there. How do we design the system, software, compilers, and languages? And finally, how do we design the algorithms and theoretical foundations? If you think about the theory of computing, I'm sure everybody here has taken a theory of computing course at some point in their lives. It's very processor-centric. Data is not the key. We count number of operations. Big O notation is all about operations, right? If we actually move to a more data-centric paradigm, maybe we'll have a different theory of computation going forward. So this really spans across the stack, and I believe this is worthwhile doing. I'll give you a couple of examples that give hope, because clearly we're not going to be able to change the stack overnight. But thinking about the adoption issues to change the stack over time may be very useful. Let's take a look at a couple of examples over here. Given that we have a short time, I'm not going to go into a lot of detail in these, but I'm going to give you examples of how we can minimally change the memory chips to get a lot of benefits in terms of the acceleration they can provide. That's almost in there. That's actually what I'm going to show you is in there in the memory chips, and people have shown after our work that you can do it in existing memory chips. And then we may talk about 3D stacked memory, but I don't think, frankly, I don't think we'll have time to talk about 3D stacked memory. So the key question is, can we minimally change memory chips to exploit the internal connectivity that's there and to exploit the analog computation capability that's there? And this is actually true for many, many memory designs. We work a lot in memory. In all types of memory architectures, you have internal connectivity and analog computation capability. I'm going to show you examples from DRAM, because DRAM is a dominant architecture that's been extremely successful out there. So let's take a look at what can you accelerate this way. So data copy initialization is used in many, many systems. And if you don't believe me, again, Google showed that only memset and memcopy, or memo and memcopy, occupies 5% of the execution cycles in all of their data center workloads. That's a lot for just 2 function calls, right? And it's not the overall data movement. There's more to data movement. So how do we actually do the copy of a page in memory today? Basically, you want to copy this white page to this dark page. We go through the processor. Basically, you disturb everything else in the system. Whereas this operation doesn't really require that much disturbance. This leads to latency issues, bandwidth issues, unwanted data movement, and cache pollution. But you could potentially eliminate that cache pollution by doing this through the DMA. So essentially, if you do a very small page copy, I would consider a 4 kilobyte page small today, because we sometimes do copies of 1 gigabyte. We do initialization of databases of 1 terabytes and terabytes, right? It takes about 1,000 nanoseconds and 3.6 microjoules. So if you show this picture to a child that's 10 years old and ask if there's something wrong with this picture, I'd recommend doing that. They'd probably tell you, why are you going through the processor for doing this? Why don't you just do this inside the memory? And it turns out memory is very capable of doing that, and if you do it inside memory, it's low latency, low bandwidth, no cache pollution, no unwanted data movement, and you get basically more than an order of magnitude speed up and almost 2 orders of magnitude energy improvement. Now, I'm not going to give you the details exactly, but if you know how memory operates, it's 2 consecutive activates. You activate the source row, which brings the data into the sense amplifiers, and then you activate the destination row, which implicitly deactivates the source row and connects the sense amplifiers to the destination row. As a result, by using the row buffer over here as an intermediate place, you move the data inside a DRAM subarray very quickly. It's negligible hardware cost. In fact, existing DRAM chips off the shelf, you can do it. There's a paper that appeared very recently in October in Micro that showed that off-the-shelf DRAM chips are capable of doing that, even though they were not designed to do so. You could actually play with the timings to be able to do this. Of course, to be able to do this reliably, I think you need to actually go and design it with slightly more design cost, but it's not a lot. Okay, so the takeaway is you can get an order of magnitude improvement and almost 2 orders of magnitude energy improvement in this case, and applications also benefit. So the thinking over here is that memory is an accelerator. We are designing all of these accelerators over here. They're all great at what they're doing, but they're all sitting on the left side of the memory bus. Why don't we have an accelerator on the right side of the memory bus? And that accelerator now has low bandwidth, high bandwidth, low latency access to large amounts of capacity. So it has the potential to be a lot more efficient. And also, we can design it such that it's really integrated with the functionalities that we know memory is capable of doing. Basically, we're using memory for computation in this case. Well, in this case, data movement, but I'm going to show you computational. Essentially, this is similar to a conventional accelerator, and we need to work on programming models for this sort of accelerators as well. So, okay, maybe you say, I cheated, I've given you no computation, this is data movement. So let's talk about computation a little bit. Basically, we can support and or not a majority operations at low cost as well by using the analog computation capability in DRAM. The idea is very simple. We activate multiple rows, 3 rows. I'm going to give you an example quickly. And it turns out this leads to between 1 and 2 orders of magnitude performance energy improvements in these bitwise operations. I believe new memory technologies can enable even more, STT-MRAM, RM, memristors, phase change memory, and actually there are works that show that this is really possible in new memory technologies. And new memory technologies can operate on minimal data with minimal data movement because they're not fundamentally destructive. DRAM is fundamentally destructive, right? Because it's charge-based and you actually destroy the data whenever you access the data. So the idea in DRAM, even we can actually do it in some DRAM chips, off-the-shelf DRAM chips, by playing with the timings also. The idea is to activate 3 rows concurrently. Now, if you do that based on charge sharing principles, you get a majority function. If at least 2 of these cells are charged, you get the charge state at the end. If at least 2 of these cells are discharged, you get the discharge state at the end. Now, I'm showing you 1 bit over here. Imagine this is an 8 kilobyte row, and imagine that you have 1,000 or more rows. This is 8 million bits within a single DRAM module. So you can actually do this on 8 million bits in parallel. And if you make your DRAM module bigger, and if you actually have a heat sink on your DRAM module, you can do even more, in my opinion. So that's a majority function. Majority function is great. You can actually convert your algorithms into bitwise majorities. But you can also express this majority function like this. If C is set to 1, you get the OR of A and B. If C is set to 0, you get the AND of A and B. Now we have a bitwise AND and bitwise NOT inside DRAM, massively parallel. Of course, we want the NOT as well to be functionally complete, and there's a way of getting NOT by actually taking the bitline bar from the sense amplifier and feeding it back to the array. I'm not going to go into detail. You can do it with a little bit more hardware cost. That's the idea. And if you do that, you get significant performance improvements in these bitwise operations, as you can see over here. So what is this beneficial for? Actually, now you have an in-DRAM bulk bitwise computation engine that's functionally complete. I believe any algorithm can be translated into it, but some algorithms are, of course, much more efficient to be translated into it. If you're already operating on bitwise operations in a massively parallel way, you can get the benefits. like bitmap indices in databases, between databases that are specially designed for bitwise operations. Microsoft has this Bitfunnel web search engine that's specially designed for bitwise operations. There are a bunch of other areas that we've examined also. I'm going to give you an example with the bitmap indices. Basically, you can, and this is our effort. Other efforts later improved the results. Based on our results, you get 5 to 7x performance improvement in query latencies based on bitmap indices. And I'd be happy to recommend you other papers that have improved on our work to actually make those even larger. If you take a database that's designed for GPUs for massively parallel bitwise operations, we actually get similar performance improvements, even larger performance improvements on the order of 12x or so. And one good thing about this is your computation capability is scaling with your memory capacity. So you can keep adding more memory and your computation actually increases as well. Okay, I'm not going to talk about these, but you can actually look at these papers. These slides will be available. This is our work, and this is the recent work that appeared at Micro from other folks that showed that you can do this in off-the-shelf memory chips. These are completely independent folks. They never talked to us when they actually submitted this work, and they showed that you can do what we described in off-the-shelf memory chips by playing tricks with memory. Okay, and these are some work that show that you could do it in phase change memory. Okay, I'm not going to talk about the second approach, which is using 3D stack memory, which is even more promising, I think, and even more, I don't want to say even more promising, even more general than what I described. But I'm going to skip to the second part of the talk very quickly. But first part essentially ends with this. I want to talk about this adoption also. Basically, we need to talk about adoption somehow, and I'd be happy to talk about this, but we need a change of mindset to actually enable adoption of such architectures. But we need to get there step by step. Okay. So let me talk about the second one over here. Basically, today's architectures are very human-driven as opposed to data-driven. I'm going to give you an example very quickly over here. How do we exploit data to design intelligent architectures? If you look at system hardware architecture design today, it's very much human-driven. Humans design the policies. They dictate how to do things. If I design a memory controller, I have a dictated policy over there. As a result, we have many too simple short-sighted policies all over the system because humans can consider only a few things when they design these policies. And as a result, there is no automatic data-driven policy learning. There's almost no learning, actually. This machine, as I said, is doing exactly the same thing it's been doing for 5 years. And that's true for all of the machines. They don't adapt their policies to what they've learned, because they don't learn. The key question is, can we design fundamentally intelligent architectures? So what is an intelligent architecture then? I believe it has to be data-driven. Machine learns the best policies, it adapts its policies over time. As a result, we have sophisticated, workload-driven, changing, far-sighted policies. And we have automatic data-driven policy learning. Essentially, all controllers are intelligent agents, data-driven agents. So the key question is, of course, how do we start? That's a massive task. We have controls all over the system. I believe we need to re-examine the design of all of those controllers. I'll give you one example from our experience. We call this a self-optimizing memory controller. We did this work about 12 years ago at Microsoft Research. The basic idea is, how do you design a memory controller that can schedule the request intelligently to maximize system performance? And if you actually ever design a DRAM controller, it's one of the worst things to design in hardware, perhaps also in software, I don't know. But basically, you need to deal with a lot of timing constraints. You need to keep track of many resources. You need to keep track of handle DRAM refresh, manage power consumption, optimize performance, quality of service. There are just too many things to think about, and I don't think humans are very good at thinking about all of these. And this is becoming more critical because if you look at an SoC like this, there are 30 or more things hanging off the memory controller, and they're all requesting stuff from the memory controller, and going forward it's going to become even worse. So basically the reality is it's very difficult to design some of these controllers, too many things to think about, and if you want to adapt to continuously changing workload and system behavior, we can give up. But wouldn't it be nice if the DRAM controller automatically found a good scheduling policy on its own? We call this the self-optimizing DRAM controllers, and the idea is that we can use machine learning inside the memory controller so that we can adapt the scheduling policy to workload behavior and system conditions. It turns out reinforcement learning actually maps very nicely to memory control. And memory controller is essentially a reinforcement learning agent. It's like a human being. We're all reinforcement learning agents. And if you actually talk to some behavior psychologists, they will say that we're only reinforcement learning agents. I don't believe that, but reinforcement learning is very important, clearly. Basically, we have an agent that observes a state, that takes an action, and that gets a reward. And over time, it learns to choose the actions at given states to maximize the long-term rewards. That's the idea, basically. And We use reinforcement learning principles to design this controller. I'm not going to bore you with all of the design choices that we do. The paper has a lot of detail, and I'd be happy to talk about the work that's going on that is improving right now the memory controllers today. This is what the human designer needs to do. They need to specify the reward functions with state attributes and actions. I believe state attributes are also discoverable by machine learning. Reward function is a bit harder. Learning the reward function, I think, is going to be difficult. So human design effort moves to reward function and actions in the end, but actions are easy. So what is the takeaway? Based on our limited set of experiments, we showed that you can have large, robust performance improvements over many human design policies in the end. Of course, there are downsides to it. How do you specify different things? What is the hardware complexity? And I believe, how do you actually change the design mindset at flow? A lot of the things that I'm describing over here require a change of mindset, because hardware design is really not used to a learning agent that's operating. How do you test this learning agent in hardware, for example? That requires some changes. But I believe we can get there step by step going forward. Okay, basically, an intelligent architecture requires all of this. I believe we really need to rethink the design of all controllers that we have in our systems today. So to get to self-optimizing data-driven computing architectures. Let me spend just a little bit time on the last one over here. Basically, today's architectures are not really aware of the properties of data, but we can do a lot more if we're actually aware of the properties of data. I call this data-aware architectures. A data-aware architecture understands what it can do to and with each piece of data. So you know a lot about the characteristics of your data. Today, we don't communicate these characteristics, at least in the general purpose way. Basically, we can make use of different properties of data to improve performance, efficiency, and other metrics. These are some examples with our limited imagination, right? Compressibility, approximability, locality, sparsity, how critical is this data, what is the access semantics of this data, and who knows what else. Today, we actually know a lot, or we can discover a lot at the higher levels, but we funnel that information into essentially instructions and memory addresses. Now, there are very limited optimizations for locality that go through relatively specialized interfaces. It's very special instructions. But the question is, can we actually come up with a much more expressive interface that can communicate a lot of this information, higher level program semantics and other things, into the hardware and the lower level system stack? We call this expressive memory because we look at a lot of memory optimizations. Again, I'm not going to go into the details of this. You can take a look at the paper. But if you actually have this sort of expressive interface across the software and hardware stack, it can enable a lot of optimizations. This is a table from the paper. I copied and pasted. For example, you can actually make approximation in memory much more efficient. You can distinguish between pools of different data. You can actually talk about tolerance towards approximation. There are a lot of other things like page placement, compression, ... And actually, we've done a case study together with NVIDIA on this one. This is just looking at the locality properties of different data. You can improve performance significantly on existing GPUs, and this is going into the next generation NVIDIA GPUs in the future. Okay, so you can actually improve hybrid memory management decisions. If you understand, for example, the tolerance of data, vulnerability of data to errors, you can actually design memory systems that are of different types that can actually scale your memory to very large sizes without actually being constrained by being reliable on everything that you have. Again, I'm going through this relatively quickly, but this gives you a lot of benefits if you understand the properties of your data. And we recently done a lot of studies on deep neural networks. You can actually find out the characteristics of different layers and different data in terms of error tolerance. And you can actually map these to different DRAM partitions to get significant performance and energy improvements. Again, I'm not going to talk about these in detail, but the papers are out there, and I'd be happy to talk about that while I'm here. Okay, so the last part is really data-aware expressive computing architectures. Can we somehow enable that? So let me conclude. I've talked about these three things: deconstruct the existing architectures. We're terrible at dealing with data, but there's hope. We can be more data-centric. We're terrible at taking advantage of vast amounts of data, but there's hope. As opposed to being human-driven, we can be data-driven. And we're terrible at understanding the properties of data, and as a result, we make component-aware decisions, but we can actually make data-aware decisions if we enable that architecture to understand the properties of data. So overall, I believe it's really time to design principled system architectures to solve the data handling problem, because we really have a huge data handling problem and manifests itself as a memory and storage, communication, and eventually computation problem. We want to design complete systems to be truly balanced, high performance, and energy efficient. This requires intelligent architectures, and I think these are the three properties of an intelligent architecture: data-centric, data-driven, and data-aware. I believe this can enable orders of magnitude improvements. I've shown you examples of this. There are a lot more examples if I had more time. You can enable new applications and computing platforms that we haven't even imagined so far. And maybe we can enable a better understanding of nature going forward, because I don't think nature is really processor-centric. I don't claim to know exactly how nature is, but I know definitely that it's not processor-centric. It's a lot more data-centric in its operation, it seems. And if you talk to neuroscientists, I think they will agree. But basically, this is the intelligent architectures for intelligent machines, in my opinion. But I think, of course, getting there is not easy. I believe we really need to think across the stack to enable this. But this doesn't mean that we get there overnight. We get there step by step by doing minimal things like I described, row clone or Mbit, where you do minimal changes to the architecture. But of course, we need to exploit good design principles that I'm not going to talk about. More than anything else, we need open minds. Okay, I think I've taken enough of your time. I'll acknowledge my students, people who fund our research. Please keep funding. And my research group for sure. Thank you very much.
Questions?
Yes, please.
A lot of information in a short amount of time. In 1 minute, just hit us on what you can do with the 3D memory.
Oh, okay.
Really interesting.
If I had more time, I would talk about it. So basically, you can build programmable accelerators in the logic layer of 3D stacked memory. And we have a lot of case studies where we've looked at, for example, graph processing workloads. You can build a message passing engine over there so that you can accelerate graph processing workloads by about 2 orders of magnitude. And you can improve the energy efficiency. I'd be happy to go into more detail. Say again? Yeah, we have a lot of papers in 3D stacked memory. In fact, right now we're looking at more than 400 different workloads in terms of how we can accelerate, what is the methodology where we can actually understand what we can offload to 3D stacked memory. So it really spans what is the maximum thing you can do with 3D stacked memory by changing the entire system, and what is also the minimal thing that you can do with 3D stacked memory by changing as little as possible in the system. And we cover a broad range in that area. I'd be happy to share all of that.
Thanks, very nice talk. I will say one word in defense of your alumnus von Neumann, since yesterday on the consoles relating to is the memory stupid or von Neumann bottleneck. In the original von Neumann report, the one that basically made the computer impossible to pattern because it all circulated quickly and so on. There is an analysis of memory by von Neumann which concludes with the following sentences. It will be clear from this analysis where the bottleneck of a computer system is and belongs with column the memory. So the bottleneck is really von Neumann because he anticipated it. So it's nice that now we are finally going to get rid of it.
Yeah. Thank you for your comment. I know very well that report, actually. I agree with that. Actually, I think, so if we had more time, I would actually give you the historical perspective also. If you go back, if you rewind 70 or 80 years back when von Neumann was designing, memory was not a huge bottleneck, but they actually anticipate that it will be the bottleneck. So if you actually go back to the picture, energy picture that I showed you, right now, memory is 3 orders of magnitude more energy hungry than computation. But if you try to do the studies 80 years ago, computation was about 2 orders of magnitude worse than memory in terms of energy. Over time, we were able to scale computation really well due to technology scaling, Moore's law, a lot of optimizations. But unfortunately, memory did not scale really well. So von Neumann predicted that very nicely. So I believe, actually, I don't want to be seen as someone who is really arguing against von Neumann architectures. I think they have their place, and they've actually played a great role in the system, and they will be there, even in processing data-centric approaches, frankly. I'd be happy to talk about that. The future is really all about heterogeneity, I think.
Okay. One other quick question, Rita.
Thank you. I have a question. It's a very interesting direction, but I wonder how to build the new architecture for the data center, data driven, and data aware. You have mentioned that using the reinforcement learning method, but how to build the new search space for the architecture's design, because the reinforcement learning we now cannot design the new search space. You should design the search space for the IO method.
So I think you're referring to the human component of the design. How does the human now become a designer, given that there are all these learning agents? So I agree that becomes a difficult part. Now the human designer needs to think differently. They need to think about how they can aid this learning agent, how they can enable the learning agent to discover different state variables, for example, to understand. I mean, this is a conversation that's longer than the time allotted for questions, I believe. I'd be happy to talk about that separately. But I agree that there's a challenge that we need to overcome to actually get there. But we've given an example with reinforcement learning. There are also more examples coming up with cache policies. I think it's possible.
Okay, thank you. Thanks.